Hi everyone, this is Samit Sankanwar. Welcome to my channel Structural Diagnostic. Every single day, the world around us is bending. Bridges flex under the trucks, skyscrapers sway in storms, wings of airplanes bend in air, and the list continues. But have you ever wondered how do engineers know exactly how much a beam can bend before it breaks? Let us understand this concept titled Theory of Bending and the Bending Equation. The theory of bending is also known as the theory of pure bending. Let us first understand the meaning of pure bending. The bending of member that occurs in the region where the shear force is zero is known as pure bending. For example, let us consider a simply supported beam with 2 point loads acting at a distance L by 3 from each end of the member. If I draw shear force diagram for this member, it looks something like this. If you observe, there is no shear force acting in the middle one-third span of this member, and this region is called as region of pure bending. Whatever bending that occurs in this member within this region is called as pure bending. And concept of pure bending is the core assumption that has been considered while deriving the bending equation. This load system is also called as 2 point load system, which is usually adopted for experiments to determine the flexural strength of beams. Now let us move to the fundamental foundation of our derivation, the assumptions considered in this bending theory. Before we move on to the mathematical derivation of the equation, it is important to understand why these assumptions exist. In reality, the behavior of a deformed body is extremely complex. These 9 assumptions act as mathematical simplifiers, removing all the second order complexities in this derivation. Let us break them one by one. First one is the beam is initially straight. Why is this important? If beam is curved initially, that will have external load effect due to initial imperfections. Assuming the beam is straight initially ensures the bending in the beam is purely due to the external loading. Second one is material is homogeneous and isotropic. It simply means the beam is uniform, having same properties at all the points within its body, and it behaves exactly the same way when it's loaded, be it in longitudinal direction or in any transverse direction. Next, material of beam obeys Hooke's law. All the assumptions considered in the Hooke's law are applicable here also. For example, the material is deformable, there is no change in temperature while loading, material behaves linearly, and there is no stress concentration. Next one is self-weight of the component is ignored. Self-weight is ignored just like any other structural analysis problem to keep it simple. Next, plane transverse section remains plane after bending. Plane transverse section do not bulge or warp during loading. If you can see in this picture, suppose this is the beam. When it is loaded, it bend in this manner, but there is no bending in transverse direction, or there is no bulging or warping taking place in transverse plane. Next, Poisson's effect is neglected. Poisson's effect is neglected to avoid additional strains in the transverse direction. You know that if we apply load in the longitudinal direction, there will be reduction in the cross section. That is nothing but the depth and width of the this beam is going to reduce, and the finally beam will look something like this. Ensuring Poisson's there is no Poisson's effect acting on this member, it will avoid additional strains in the lateral direction. Next one is Young's modulus of the elasticity is same for compression and tension. Having same E value ensures that the neutral axis passes through geometrical centroid of the cross section. Next one, beam is prismatic. This assumption ensures there is no stress concentration. Beam is prismatic. It only means that there is no change in cross section. If there are any sudden change in the cross section, there will be stress concentration. In order to avoid that, it is assumed that the beam is prismatic. Next one is loading is done about axis of symmetry. This will ensure there is no twisting of the member during loading due to unsymmetrical loading. Now let us go ahead with the actual derivation of the bending equation. First of all, let us consider a section which is under pure bending within a beam section. Now remember, this ABCD is a longitudinal section and not a cross section. Here AB represents the top fiber, EF represents a fiber which is at the neutral axis, and GH represent any fiber which is at a distance y from neutral axis, and CD represents bottom fiber. Initially beam is straight, that is EF is equal to GH. In our previous slide, when we were discussing assumptions, it was stated that the beam is initially straight. That assumption comes into picture here, that before loading, fiber length, that is EF, which is considered within this section, is going to remain same as that of fiber GH here. Now when the loading is applied, the beam bends in similar manner to this, creating radius of curvature R with having theta between these two lines here. Then this fiber AB becomes A dash B dash. EF remains EF because this is fiber which is at the neutral axis and there is no change in its length. And GH fiber becomes G dash H dash and CD becomes C dash D dash. Remember, the strains in all the fibers are longitudinal strains. We saw one more assumptions in the previous slide, that is Poisson's effect is neglected, means there is no transverse strains in these fibers. These are all the longitudinal strains. Now if we consider EF, that is the fiber which is at neutral axis, its length will be calculated as R into theta, because assuming this is arc of a length which makes angle theta here at the center, then length of this arc EF will be R into theta. Similarly, if I consider length of this arc, that is G dash H dash, it will be R plus Y into theta, because this is radius of curvature R up to neutral axis. Then this G dash H dash is at a distance Y from neutral axis. Therefore, length of this G dash H dash fiber from center will be R plus Y into theta. Now, if I consider the longitudinal strains coming up in this G dash H dash fiber, it will be, we know that a strain is calculated as change in length, ratio of changing length to its original length. Therefore, change in length that is taking place in this fiber will be G dash H dash minus initial GH upon initial length, that is GH. We know that G dash H dash is R plus Y into theta, that I substitute here minus as it is, and GH would be R into theta because we know that EF is equal to GH here. Upon solving this, I get here, when I multiply this theta inside, it will be R into theta plus Y into theta, plus R into theta minus R into theta get cancelled here, and what remains in the numerator is Y into theta, and in the denominator it is R into theta. Now here theta get cancelled and what remains is Y by R. Therefore we have a equation here now, that is strain in this G dash H dash fiber is nothing but Y upon R. Let us call it as equation number 1. Now we know that stress is directly proportional to strain. I can write it as stress is equal to Young's modulus into strain, where Young's modulus is constant of proportionality. And we know this relation from our previous lectures. Now, can I write this equation as strain is equal to stress upon Young's modulus? And I'll call this equation as equation number 2. Now, from our equation number 1, we know that strain is equal to Y upon R. Since we have same term in the left hand side of both this equation, I can equate right hand side of both the equations. That comes out to be sigma upon E is equal to Y upon R. If I rearrange these terms, I'll get sigma upon Y is equal to E upon R. Now I'll introduce a new term, that is sigma B. Sigma B is nothing but bending stress. If you can see in this diagram here, there will be bending stresses induced in this section of the beam when the loading is applied. Top fiber experiences compressive stresses and the bottom fiber experiences tensile stresses. And I call these stress as bending stress, indicating by this symbol, that is sigma B. Here I'm sending this y on the right hand side, that will be sigma B is equal to E upon R into Y. Here E upon R is constant for a beam. Therefore, I can say that bending stress is directly proportional to the distance of any fiber from the neutral axis. Therefore, variation of bending stress is linear. If I want to show you this, at y sigma b is equal to 0. Means if I substitute y is equal to 0 in this, I'll get 0 stress. Therefore, this is compressive stress and this is tensile stresses. If you carefully see here, when I apply loading, this top fiber will reduce its length and bottom fiber uh, expand its length. Therefore, there will be negative strain in this and there will be positive strain in this. Therefore, this compressive stress is on the left hand side and this tensile stress is on the right hand side, simply indicating they are opposite in nature. And at neutral axis, the stress is totally zero. Now, to proceed further with the derivation of our bending equation, let us consider a cross section of the member. This is a typical cross section of a rectangular beam where NA represent the neutral axis. Now from our previous slides, we have got this relation that sigma B is equal to E upon R into Y. And also, to simplify this, we can say that stress is directly proportional to the perpendicular distance of any fiber from the neutral axis. Now let us consider dA, which is an elementary cross-sectional area at a distance y from the neutral axis. So this is that elementary cross-sectional area at a distance y from neutral axis. Remember, stress is nothing but the resisting force acting per unit area. Similarly, there will be an internal resisting force acting on this elementary area that produces sigma b, that is nothing but bending stress. If I want to explain you further, here, when the loading is applied, beam tries to bend in this manner, producing compressive stresses at the top fibers and tensile stresses at the bottom fibers. This resisting force dP, which is acting at elementary area dA, will try to resist this bending. Therefore, sigma B can be termed as dP upon dA, that is nothing but resisting force acting per unit elementary area here. I can further write by rearranging this equation as dP is equal to sigma B into dA. Now from equation 4, we know that sigma B is equal to E upon R into Y. I'll just substitute sigma B by E upon R into Y in this equation. Then I'll name this equation as equation number 5. This dP will produce a resisting moment, that is called as dm, which is equal to dP into y. We know that this resisting force dP, which is going to act here, will produce a moment here, which is at about this neutral axis, which is at a distance y from neutral axis. Therefore, that elementary moment dm, I'll consider it as dP into y. This we got from our previous slide, that is elementary moment is equal to elementary resisting force into the perpendicular distance of any elementary area from neutral axis. Now, all such elementary moments throughout the beam will contribute to the moment of resistance, that is indicated by mr, which is nothing but moment offered by beam material to resist the bending moment due to applied external loads. So this is the cross section of the member and this is the elementary area that we have considered. Any resisting force acting in this elementary area would produce a moment, elementary moment dm. Similarly, if I consider elementary area throughout this member, that would together produce moment of resistance. In order to have a combined effect of all these elementary moments, I will have to integrate this term. Therefore, when I integrate this elementary moment, integration will be done in this manner, that is integration of dp into y. Therefore, dp can be replaced with this term from equation number 5 that we saw in our previous slide. Now here E upon R is constant for a particular beam, therefore I will take this term outside. Then I'll have integration of y square into dA. This is nothing but second moment of area, and there arises one more term to replace this integration of second moment of area, that we call it as I, that is nothing but moment of inertia. Therefore, total integration of this small elementary moments will give me moment of resistance of the entire beam, that is equal to E upon R into I, replacing this integration of y square into dA by letter I. Now I'll rearrange these equation as mr upon I is equal to E upon R, and I'll call this as equation number 6. Now I want to compare this equation number 6 with equation number 3. Our equation number 3 was sigma upon E is equal to y upon R. I will rewrite this equation 3 like this, bringing y down and sending this E up here. Therefore it will look something like this: sigma upon y is equal to E upon R. Now if you compare this equation number 3 with equation number 6, you can see E upon R is equal to mr upon I here, and E upon R is also equal to sigma upon y here. Therefore, I can write this equation as mr upon I is equal to E upon R as it is. Then, since this E upon R is also equal to sigma upon y, I'll write this as sigma upon y here. Therefore, now we have arrived at the our final bending equation, that is m upon I is equal to E upon R, which is equal to sigma upon y. Now to wrap things up, remember that while the core engineering formulas we use every day are built on ideal assumptions, knowing exactly when, where and how those assumptions break down is what separates a good engineer from a great one. If you found this breakdown helpful and want to master more core concepts, structural design, workflows, and practical engineering insights, make sure to hit that subscribe button right now. Welcome to the community here at Structural Diagnostic, where we decode the complex math, simplify the mechanics, and diagnose structures from the ground up. Thank you so much for watching. Keep learning, keep designing, and I will see you in the next video.